general relativity, step by step. Last time I showed that proper time was the same for all observers between two events, was the same observers between two coordinate time events, t1 and t2. Which does not sit well with the fact that two objects at rest, as I showed here, have got an oscillating distance between the two, as measured by proper distance between the two. So what I'm going to do now is I'm going to develop that idea, and I'm going to show how we can talk about the polarizations of the gravitational wave, and I'm going to show how we can do this using the Riemann-Christoffel curvature tensor. Now, all the way back in screencast, actually I'm going to pinch in, here we go, screencast 137 I think it was, I showed the following formula. d2n by d tau squared, no, it's not squared, I'm quite sure where I got squared from, let's just get rid of that, component alpha, equals, and I'm writing it out again very carefully because mu, nu, sigma, there are lots of different sign conventions and I want to make sure I've got it right. Sigma, u, mu, n, mu. So this is our little expression of the tidal forces exerted by the curvature of space, effectively, curvature of space-time. We write it out like this. So let me just take you through what all the terms mean. Tau from here is proper time. N was the separation vector between our two particles, separation 4 vector between two particles. That's this term here. U was the 4 velocity, the relative 4 velocity, relative. And of course this monster here, alpha, mu, nu, sigma, was the Riemann-Christoffel curvature tensor. Riemann-Christoffel curvature tensor. Alright. Alright. So we had a little particle here, and we were interested in what happened to different particles at different separation 4 vectors from our particle in the centre there. And we have this formula here, and I'm going to apply this formula, this formula here, to gravitational waves. So I'm gradually going to simplify it using the linearization, using the simplifications that both the linearization of the field equations and also the particular gauge that we chose can give us. We're going to use those simplifications. So the first thing to remember is that t we may as well replace with we may as well write t instead of tau. There we go. Because as I showed in the last screencast, all the observers have proper time at the same rate. So d2n by dt, dt squared, component alpha, equals minus r, I'm just copying from here, alpha mu nu sigma u mu n nu. There we go. Isn't that beautiful? Now I'm also going to choose the 4 velocity u. I'm just going to choose 1 0 0. So at rest. So we've got our particle here, and we've got another particle at separation n, and it's going to be at rest in terms of yes, it's going to be at rest because the 4 velocity is going to be 0. So that tells me that I've got d2n, oh dear, let me pinch in on this a bit, I don't like the new pen, d2n by dt squared now equals, now I may as well specify here that sigma must be equal to 0, and which other one, mu has got to be equal to 0, because it's only the 0 component that's non-zero. It's only the time component Yeah, the only non-zero component of the fall velocity is the time component, which is a 1. So that means that I can, in this summation here, I can ignore a sigma that's not equal to 0. And I can ignore a mu that's not equal to 0. So that's a huge simplification. It means I can ignore the summation. So it's minus r alpha 0. Nu is still free because that's attached to the n. 0 that's just a 1, that's just a 1, n nu. Okay? And now I'm going to make a stab at evaluating the Riemann-Christoffel curvature tensor. Let me write down the equation I've got here from screencast, again from screencast 137. The definition of the Riemann-Christoffel, well, I'll write down the definition of minus the Riemann-Christoffel tensor. I'm just copying down from screencast 137 here. I took a screenshot and I'm just copying it down. Equals minus di by di x nu. You see, I'm putting the full terms mu and sigma in just because I want to be able to copy it down. It's always as well to do that with tensor equations. Always write down the equation in its full generality and then simplify to the particular case you're interested in. Christoffel symbol, alpha sigma nu, and that's a minus, plus di by di x sigma, Christoffel symbol, alpha mu nu. Now there's also cross terms here, which I'm going to ignore because I'm only working to first order. Okay, so we know that sigma equals, from here, sigma equals 0 and mu equals 0. So that's minus di by di x nu, Christoffel alpha, sigma equals 0 for that, and that's a nu there. That makes me nervous because that makes me very nervous. That makes me nervous because I've got a nu and a nu both in the downstairs position, and I thought, oh, it doesn't matter because I'm considering a particular value of nu, but I'm not. That's a mu. See how I caught that mistake? That's a sigma and that's a mu, not a nu. And have I got this one wrong? No, that's right. Sigma and mu, mu, nu. So yes, we've got a sigma, a mu, and a nu, a sigma, a mu, and a nu on the bottom. And here we've got a sigma, a mu, and a nu on the bottom as well. Let me just write that out a bit more neatly. That's a no, that was both. They were both wrong. Sigma mu plus di by di x sigma alpha mu nu. That's better. That's better. And now I'm going to specify that sigma equals 0 and mu equals 0. So I'm going to pinch in. Sigma equals 0 and mu equals 0. So that means that these two terms here are zeros. And that also means, what am I doing here? What am I doing? Just a minute. Sigma equals 0 and mu equals 0. So sigma equals 0, so that's di x 0, and the other term is mu, which is this one here. Why doesn't it delete it? There we go. And that's a 0. So that's equal to minus di by di x nu alpha 0, 0 plus di by di t alpha 0 nu. Whew. Right, and what I'm going to do, I won't do it in this screencast because it's already gone too long, minus r alpha 0 nu 0 equals this. I'm going to evaluate that for the linearized case for the gravitational field equations in our particular gauge that we've been working on for a few screencasts now. So I'm going to next time I'm going to evaluate this. And we'll see, it's a bit of a pain, but we can do it, and yeah. Okay, stop.